All right, 4.5 is on basis and dimension. Well, first up, let's look at the definition of basis. A set of vectors S in a vector space V is a basis of V if S spans V and S is linearly independent. So if you think about what this means, it means S has enough vectors in it so that you can get everything in V as linear combinations of them, and it doesn't have any extraneous vectors in there. So for example, in R2, if you had the set 1, 0, 0, 1, written like that, that is a basis of R2 because it's got all you need to get any vector in R2 is a linear combination of those two guys, and there's nothing left over. If I put in another vector, say 1, 1, this would still span R2, but it's no longer linearly independent. So if I add extra stuff in there, it's no longer a basis. So let's get this guy out of there. And a couple of facts. If S is a basis of V, then the number of vectors in S is the dimension of V. That makes good sense up here with this example because R2 is a two-dimensional vector space and it's got two vectors in its in a basis. And also, a vector space can have many different bases, usually infinitely many of them. But all of them will contain the same number of vectors. So, if I wanted to come up with a different basis of R2, I could use this vector and that vector. That would form a basis, and it's still just two vectors. One other note here, the plural of basis is bases. It's written the same way as the word bases, but it's when you're talking about the plural of basis, it's bases. It rhymes with Macy's, not faces. All right. Now, the reason bases are important is because they're the most efficient way to describe a vector space. And this includes specifying a particular subspace of a given vector space. So let's look at standard bases. The standard basis of Rn is this set of vectors here. This is n vectors total, but the first one has a 1 in the first position, then a 1 in the second position, and so on until you get to a 1 in the last position. So in R2, this is the standard basis. In R3, this is the standard basis. For vector spaces consisting of matrices and polynomial, they're defined similarly. Like for M22, the standard basis would be this, 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 don't need a comma, and this. Notice that's a four-dimensional vector space because it's got 4 elements in there, and each one of the vectors has 4 bits to it. For P3, the standard basis would be, I'm not really sure if there's an ordering on this or not, but standard basis would be, let's see, that's polynomials of third degree and smaller, so x squared, x cubed, x squared, x, and 1. All right. So what I want to look at next is if you're given a set of vectors, how do you determine if it's a basis? Well, if you go back to the definition, you have to make sure that the set spans V and that it's linearly independent. So if you're dealing with Rn, then it's actually, you can think of this slightly differently. In order for a set of vectors to be a basis of Rn, it has to have exactly n vectors, and they have to be linearly independent. And there are a couple of different ways you can check this stuff. What I want to do, though, this is several examples from a different textbook. I want to look at, maybe not all of them, but let's look at these guys here. Which of the following sets of vectors are bases for R2? Okay, so first up, for it to be a basis of R2, it has to have exactly 2 vectors in it. So we can eliminate this one, and we can eliminate this one. these have too many vectors. And therefore are not linearly independent. Now these others, in R2 it's actually really easy to look at and tell. This one right here, we've got two vectors and they are linearly independent. So that's a basis. Now down here, we've got two vectors. Are they linearly independent? No. Actually, yes, they are. For a second there, I thought that they weren't, but they are linearly independent. And how do you tell? Well, if you've only got two vectors, then if they're linearly dependent, it means that one's a multiple of the other. And this is, I think they're trying to throw us off here by making this almost doubling this. So these are two vectors, they are linearly independent, therefore this is a basis. Now, if this negative weren't here, it would not be a basis because then it would be 1, 3, and 2, 6, and they point in the same direction. If there were a negative on the 6, it would not be a basis. Okay, let's go to problem 2 here. Which of these sets of vectors are bases for R3? So in order to be a basis, it has to have exactly 3 vectors for R3. So we can throw this one out. Now, the problem with that one technically is it doesn't have enough vectors, and therefore it can't span all of R3. Let's see. This one has 4 vectors, so it can't be linearly independent. Ditto for this one. This one right here, though, it has 3 vectors. But the question is, are they linearly independent? Well, we have to check. I'm going to look at them at first and see, is there an obvious linear combination among them? What I mean by that is, if this happened to be double that or triple that or something, then automatically not a basis. So let's use octave to work this out. The vector that I'm going to deal with here is 3, 2, 2, negative 1, 2, 1, 0, 1, 0. Now there are two things I could do here. I'm going to stick with what we've been doing first and just put that in and see if it has a non-trivial solution. Let's see. We have 3, negative 1, 0, 2, 2, 1, 0, 2, 1, 0, 0. Oh. I left off a 0 on this first one. All right, when I reduce it, I get an identity matrix and then zeros, and that tells me that they're linearly independent, and so therefore this is a basis. Now the other thing you could do, since that's a square matrix, I could have taken the determinant. What I'm going to do, I'm going to come back in here and I'm going to put in just the coefficient matrix. And when I get a non-zero determinant, that tells me that that it's linearly independent. Why does it tell me that? Well, remember, if you have a non-zero determinant tells you that it's going to row reduce to the identity. So row reducing to the identity tells you that it's linearly independent because you've only got the trivial solution. All right. Now let's look at 3. Which of the following sets of vectors are bases for R4? So we can throw out anything that has fewer or greater than 4 vectors. Let's see, this first set has 4. Second set has 3, so that can't span R4. This has 5, so those can't be linearly independent. So we've got two of these that we would have to check. So let's do that. I entered this in, but I put each vector as a row instead of a column. I'm going to add that to it, some zeros, and then I'm going to look at the transpose of that. Okay, so that's the vector that's the matrix that we want. Let's take the reduced row echelon form of it. When I row reduce that, I get the identity. So this is a basis of R4. And let's do the last one. I know this is getting a little long, but let's do it. I'm gonna do the same thing. I'm gonna enter the vector. Let's see, 0, 0, 1, 1. So again, that's the transpose of what I want. So transpose of M. Let's double check that that's what we want up there. Yeah, the first vector. This vector here is my first column. This is my second column, and so on. I want to row reduce this. I want to row reduce the transpose, not the. So when I row reduce that, I get an identity. So this one again is a basis. All right, so we'll stop there.